Trees are pretty hard to build, in my opinion. So why not get code to do it for you? In addition, this is a pretty good exercise in C-frames and their transforms and recursion. So stay tuned if you want to learn how to make these procedurally generated trees, and like and subscribe if you enjoy. So this video is going to be a hybrid of my shotgun video and recursion video. But the way that we go about creating this procedurally generated tree is going to be a little bit different. We're going to do it iteratively. So we're going to start by getting one simple feature done and kind of iterate on it so you guys can develop intuition for how the system should work and how you should develop this algorithm so you can eventually extend it on your own. So I'm here in a blank base plate going to create my new base part, and I want this to be wood colored and shaped. So we're going to make it look like wood. And the first thing we want to note, this is a very like pedantic thing, but I think it's pretty important, is notice how that the wood grain, so like the lines of the wood are going, left to right here, like left to right here, also here, and then these are like going like this direction, like I don't know, Z in the Z axis, and they don't really have a matching like top. So the tree should sort of be shaped like this. This should be like a branch. You can rotate the branch a little bit too. So this should sort of be our like initial tree branch because the grain is going in the right direction. And I don't know why the wood texture works like this, but this is what we have to work with. And to make it a little bit easier on ourselves, we're going to show the orientation indicator here. Um, and that just shows us which direction this wood block is facing so that we can better, analyze it. So the forward direction is this way, the top direction is that way. So we know that the tree should grow in the positive x-axis because the forward is the z-axis. So this little blue line is the z-axis, this local z-axis of this wooden block. And it just so happens that it's more or less aligned with the z-axis of the world right now. Now the x-axis, on the other hand, is going to be a little bit different because we rotated it a little bit. So because we rotated it, the x-axis is going to be to the right of the forward and up. So forward is this way, up is going left of my screen right now. So then X would be going up. You see this red little dot? This red means X. So X is in this direction. So that's where we want our tree to grow. So the first thing I'm going to do is I want to just make a simple little script to grow the tree upward. So basically, we're going to create a bunch of different branches that stack on top of each other in the upward direction. Should be pretty simple, but that will be a good starting point. So first of all, I'm going to make sure this block is anchored. Anchored, cool. Then I'm going to group it using Control G, or I guess Command G, because I'm on Mac now, which is kind of weird. And then I'm going to just, I don't know, rename this to 3. And then this part is going to be our root. Call it root. So it's like the base of the tree. And I'm just going to add a script in my tree. And we're going to get a reference to the tree, which is just equal to script dot parent. And then we're going to get a reference to the root, which is tree dot root. And this is not very expandable, I guess, to like, a bunch of different trees, whatever, because we're parenting the script here. If you really wanted to make like a good, robust random tree system, you either make a plugin or put a script into server script service that you could then use tags or something to auto generate. But for now, since the focus of this video is more on the algorithm development and the C-frame transforms, we're just going to parent the script to the model just because that's the simplest, the like least theoretical overhead. So that's what we're going to go with. So now I'm going to create a function, local function, generate tree. And then this function is going to take in 2 parameters, the parent branch, which is going to be of type base part or part. And honestly, it doesn't really matter for this case. And then we're going to do iter, which is like the number of iterations, is going to be a number. So this is going to be our recursive function. So recursive, if you guys don't know or I don't remember, please watch my video if you haven't. It's pretty good as well. It basically means you're calling the function in itself. So we're going to call any number of generate tree calls inside of the generate tree recursive function. Now you could do this using a for loop. It's just in this case, it's a lot easier to use recursively. Also, trees sort of have a recursive structure because each branch has another branch and that branch may have two branches. It kind of grows like recursively. It grows like a tree. I mean, in computer science, we literally have a data structure called trees that have sort of a recursive structure, and they're called trees because they look like trees. So, yeah. And basically, what we want to do, at least initially, is initially call generate tree. So this is the first generate tree call outside of the function definition. This is what's going to kick off everything. And our parent branch, our initial parent branch should be the root, and the number of iterations should be 0. So we start with 0 iterations, and then we need to, in order to keep this function from running forever, because unlike a loop, a recursive function, I guess, will just run forever unless you stop it. You have to explicitly stop it. So we're going to start, and we're going to create a variable called max iterations. It's going to be equal to, I don't know, let's just say 5. And in here, we're going to check if iter is greater than max iterations, then we're going to, oh, sorry, I'm used to writing Python, so keep on putting the colon there. Then we're just going to return. So this is going to prevent our function from running infinitely, because if the function ran infinitely, it would freeze your Roblox. It would be kind of annoying. So we definitely do not want that. And now we need to actually do the generation. So before we actually get to the scripting, let's first set our pivot in our wood block, because right now you can see the little blue dot. It's in the middle of our block. And honestly, it's just fine in the middle, but personally, conceptually, it's easier for me to move the pivot to the bottom of the block. That way, when we're positioning subsequent blocks, we can kind of just put the next pivot on top of the block. I think it just makes a little bit more sense conceptually. And it might be easier to work in CFrame, might not. I don't know. It's just what I like. You can do what you want. It might be a good exercise to try to put the pivot at a different spot and see if you can get the same behavior. Because at the end of the day, it doesn't really matter that much. So, first thing we're going to do inside of here is get the pivot. So, and we're going to do this above the base case. By the way, this little if and then return is a base case when you're done, because we're going to need to put the leaf in the base case. So, we're going to need this pivot information later. So, I'm going to say local pivot equals parent branch get pivot, and then local origin equals CFrame.new. We're going to say, so the pivot is just getting the pivot CFrame, so it's going to be like this thing at the bottom. And then we need to get the origin of the next block. So this is the current pivot of the parent, and this is the origin of the like new branch. So this origin needs to be transformed. So we're here, and we need to get all the way up here. Now, the naive solution here would be add, the size. So let's just see. It's going to be the x size. So the x size is, where is these? Oh, here. Go down here. So the x size is, where's the size? Okay, here's size. X size is like 4. So this is like how tall it is. So you take the pivot and then you just add 4. Oh, I just realized I made the pivot of the model. We don't really care about the pivot of the model. You need to go to the root block and then set the pivot down here. That's my bad. So recap, a root part needs the pivot to be at the bottom, at least for my example. And this part has size 4. So the naive solution would be to add 4 on the y-axis to get blocks that stack on top of each other. The only issue with that is once we eventually start doing rotations and, different scales, whatever, that's not really going to work out too well because it's just going to go upwards regardless of where the orientation of this branch is. So we need to stick in the local space of this block. Local space meaning that, for example, if I move this block to the side, I can like scale it, and you see how the scale handles stay aligned with the long axis of the wood. So this is the x, like the local x axis of this block. So we want to stick to that. And using CFrames, it's not that bad. So we're going to make a CFrame like origin. It's going to be in, this is just a arbitrary coordinate. It's not going to be in global or local space initially, I guess. And this is going to be negative or positive actually in this case. Vector 3 dot x-axis times parent branch dot size dot x. So basically, we get the x-axis. So in this case, it's going to be, up and down, like the long axis of our wood grain. And then we're multiplying it. So this x-axis is just a synonym for 1, 0, 0, like vector 3.new 1, 0, 0. And then we're multiplying it by the size. So we're basically creating a new vector with everything 0 except for the x-axis. So it'll start at the bottom and then go all the way to the top, which is exactly what we want. But right now, it's not really doing anything. So we need to make our new branch and then move it to that new origin. And since the pivot is at the base, we don't have to offset where it moves. We just move it to this new origin position, just random. It should be perfectly good. So we're going to create a new branch. So local new branch equals parent branch clone. So we need to clone the parent. And then we're going to set, before we parent the new branch to the tree, we need to just set all of its properties. So in our case, the only property that we need to do is pivot it. So we're going to call the pivot to method. And this takes in a CFrame, our new CFrame. So what we're going to do is we're going to pivot times origin. Now, pivot times origin is the literally exact same thing as doing pivot to or to world space origin, same exact thing. If you look at the docs in CFrame, it literally tells you that. Only reason I'm using a multiplication sign here is because we're already in a method call, and it just looks a little prettier to do that. And if you think about it, we're basically taking the pivot, so the pivot like coordinate space, like local to our parent branch, and then we're transforming the origin into this space. So whatever's to the right is going to be put into whatever's to the left and kind of transform to that local space. So that should work fine. I can explain more once we actually run it and verify that it works. And then we're going to set the new branch dot parent equal to the tree. You could do it to the you could do it to the parent branch. Doesn't really care. I'm just going to do the tree. So they're all within the model. And that should be perfectly fine. Then after that, we need to do generate tree. We're going to do parent, and we're going to pass in the new branch. So this is where the recursion starts. This is the recursive step. So we take our new branch that we just created, we make that the parent branch, and then we add one to iter. So this is very important too. Make sure to add one to iter. So we add one to iter, and that basically means that eventually we'll reach our base case and we will terminate. But before that, we'll run, I don't know, 5, 6 times. So I'm going to run. You can play if you want. I'm just going to run. This is all you need to see. And then look at that. We have our post. And just to double check that these C-frames are good, I'm going to hold Alt to hover over the individual blocks instead of the entire model. So Alt. You see this one, these two roots don't really intersect. They're literally right on top of each other. Like there's no space between them. They're exactly right on top of each other. And that's great. That's exactly what we want. So just to recap, basically we get the pivot. So we get this position, we offset it, or I guess we get this little blue position here. We offset it by the length of the block. So we get to the top of the block. And since the new block will have its pivot at the bottom, we can just pivot it to that position. And then what we also have to do is multiply it by we have to multiply the origin by the pivot, which transforms this world space object. Or I guess this vector, I mean, it's in world space, I guess, because it's just, a normal vector, but you can think of it as just like a raw vector. It's not really in any space. So this vector here gets transformed into the world space relative to this other C-frame. I keep on saying vector and C-frame. They're all just transforms. In this case, we're dealing with C-frame, so sorry for my ambiguity. But yeah, so, and this will make more sense once we add some rotations to actually make it, rotate like a tree, and we'll get to that. Now let's move on to rotation. So Above the new branch, let's do some calculations to get the rotation. First, we're going to start out by just making a kind of naive, just curving rotation that doesn't actually randomize and doesn't really go around. So we can start by creating like local rotation equals CFrame, CFrame dot angles. So CFrame dot angles is equivalent, as it says in the docs right here, very helpfully, to Euler angles x, y, z. So it applies the x first, then the y, then the z. This is important for what we're doing because we want x to apply first because if we look at our block again, x goes through the long axis of the wood. So we want the x, which is like the rotation about the axis, to go first, and then we want to rotate it to the left or to the right so it kind of curves off to the side. And we can actually show each one of those rotations now. So one important note, keep in mind this is in radians. So let's just do a can't even remember my radians. Let's just do like a 30-degree angle, which is going to be math.pi divided by 6. So 30 degrees is math.pi divided by 6. 45 degrees is math.pi over square root of 2, I believe. And then 60 degrees is math.pi over 3, just for some simple numbers. There's also this function, math.rad, that converts any angle in degrees into radians, and we'll use that in a little bit. But for testing, this will work fine. And I'm also going to make everything on a new line just so it's easier to understand. So it's going to apply the x first, then the y, then the z. And right now we're just applying like one rotation. You know, if you wanted to, you can multiply this by iter or something. So it just, rotate around. Oh, but obviously I didn't apply the rotation to anything. So in order to apply the rotation, it's literally as easy as multiplying by rotation. So you can experiment with switching these values around, but this is the order that worked out for me. And I would say some like crazy mathematical, theoretical explanation of how I got this. I just kind of swap things around. In hindsight, it kind of makes sense. You have the rotation first, and then you put the rotation into, you offset the rotation by the origin. So this, just C frame with 0 position gets offset by this C frame with 0 rotation, just position. And so basically the rotation gets moved up to wherever this value is, and then that all gets converted into world space. But yeah, if you don't know what's going on here, just play around with the values, see how it goes. But this is just applications of transforms going from, so the right one happened right to left. So it happens, rotation happens first, then origin, then pivot. And we can run this. You can see you get some rotations because we're doing like multiplying by iter. It goes like too quickly, but you can see that the x-axis, the one that goes through the wood, that's the one getting rotated. So that's great. So now what we can do is let's go randomize it. So radians goes from 0 all the way to 2 pi. So what we can do is we can do math.random, which gives us a value from 0 to 1, and we can multiply that by 2 times math.pi. So this will give us a random rotation from anywhere from 0 to math.pi, because we're basically scaling whatever math.random gives us to 0 math.pi. This works great. And you could also do this by saying math.random between 0 and 360 and then converting that to radians, but this works well. I don't care. So here we go. So we have random rotation on the x-axis. That works wonderfully. And now, since it applies x first, so since we rotate it first on the x-axis, we can just apply either y or z rotation. Honestly, it doesn't really matter because if you think about it, y rotation would be rotation like this. You see where my mouse is moving, like kind of left to right here. And then z rotation would be like this. I think I mix those up, but again, it doesn't really matter. Since our blocks are symmetrical, like radially, it doesn't really matter that much. So what we can do is we can create our angle at which it will rotate. So I guess first thing we can do is, again, for demonstration purposes, just do a fixed angle. Do that. And yeah, look at that. So we actually are getting kind of like a tree shape now. So it's rotating a fixed angle, but since our x rotation is random, it actually gives us a random rotation like entirely. It kind of looks like a spiral. Let's just see if we get the same one again. Oh, I spawned it. Yeah, so it's a little bit different. That's because the X rotation is random. So it actually, sort of works pretty well already, even though we haven't really randomized this value. And we can randomize this value now. So this is the part at which you have some creative freedom, at least for the randomization. I don't really know like a very good formula for this. This is the one I kind of came up with. I also got chat to help me a little bit because I could not be bothered to make a realistic like tree rotation algorithm thing. But what we're gonna do is we're gonna take the input of the progress, which is gonna be the iter over the max iteration. So basically, how far are we in the tree? And then what we're gonna do is we need like some sort of base angle. So okay, local base angle. And a value that I found that worked well enough for me, good enough for me, is 45 degrees. And then we're going to make our base angle here. Local base angle is going to be equal to math.lerp. So it's going to go between, we're going to go between 0 and then base angle. So, and the t value is going to be progress. So math.lerp, basically when progress is 0, we're going to give you 0. When progress is 1, we'll give you base angle. Anything in between 0 and 1, we give you a linear like interpolation between 0 and base angle. So let's say progress is at 50%. So we're at iteration, I don't know, 2. I guess there's no real 50% progress. You get what I mean. So iteration 2, for example, it would be, I don't know, like 20 degrees. So the taller you get in the tree, the more extreme the base angle is going to get. And then what we're going to do is we're going to add some randomization to this base angle. So say local variation equals 20 times 1 minus progress times 0.5. So basically, the more we go up, the less variation there is because we're doing 1 minus progress. So when progress is like 1, there's going to be like 0 variation. But lower it is, it's going to be a little bit more variation. Again, this is kind of arbitrary. I don't really know what I'm doing, but it works well enough. And we're going to do our local droop angle. That's my scientific name for the angle at which the branches droop down. I know, it's great. We do base angle, and then we're going to multiply, or we're going to add that to math.random negative variation to variation. So this just gives us a negative value between like the two angles and degrees. But since we're dealing with angles and degrees, we're going to do math.rad droop angle. So this converts it into a radian value. And so again, if it's easier for you to work in the degrees, just always convert it to math.rad. But all of these CFrame functions, they all take angles in radians. So just remember to do that. So let's test that out. See how it looks. This is looking kind of like a tree. You see the droopage? It looks pretty good. I'm not gonna lie. I kind of like that. So again, I encourage you, play around with these to get a more tree-like shape. And if you find something cool, comment it down below. I will check it out because I am not an artist. I'm a programmer, and this is my tree, and I love it. It's beautiful. Don't judge. Okay, so we're getting there. We do need a little bit more, and that's in the department of actually generating multiple branches. This is another one of those things that I will say totally up to you and how you structure this. My logic is we want to generate a branch. Like we want to generate at least one branch every single time. That is non-negotiable. We'll do one generation. But otherwise, we might want to like branch off multiple times. So I'm going to create a local chance variable. And this is again pretty arbitrary, but works well enough. So it's going to be math.max 0.1 and then 1.2 minus progress times 0.8. So basically, the farther we did I spell progress wrong? Yeah, I did. The farther we get up the tree, so the higher progress we get, the less of a chance there is to spawn new branches. But then we still give us like a chance of 0.1 if it's like low enough. This math.max probably isn't really necessary. And then we're going to say, well, math.random is less than the chance. What am I pressing? My bad. Well, it's less than the chance we need to generate the tree with the new branch and then iter plus 1. And again, we don't have to add any more to iter because we're still at the same like tree height. We're just branching off in a different direction. And what we're going to do is we're going to half the chance. So I'm going to do chance times equals 0.5. So every single time we go around, it becomes half as likely to get a new branch. This just makes it so that we don't get like, a bunch of like arbitrary branches. It's harder to get new branches, but it's possible. It's harder. Again, this chance variable is arbitrary. This just means the higher you go up, less chance there is for more branches. But we run this, and there we go. This actually sort of looks like a tree. But as you might notice, these branches are chunky. They're very, very chunky. That's less than ideal. We want to have tree branches that kind of taper out as they go up. And that's pretty simple. Since we have the parent branch, we have the child branch, we're able to edit the size on the fly and figure that out. So let's create our local new width. This is going to be the kind of like radial width of the tree. It's going to be new branch dot size dot y, and then you can multiply this by whatever you want. I'm going to say 0.7. So it's going to be 70% of its parent's width. Then we're going to do new length, and this one is going to be the size dot x, and that's because, as we showed earlier, the x size is the length size, lengthwise of the tree. Now, usually in Roblox, z is the forward direction. Z, it would be like the z size, but since the wood grain in the material kind of goes this way, we're kind of limited to that. If you use your own custom materials, whatever, it'd be fine, but we're dealing with arbitrary constraints, but it honestly doesn't matter. Just trial and error will get you there. For this one, I'm going to do 0.9. So it's going to be 90% of its parent. So it's going to get 10% smaller every single iteration, which that works great. And so now we can set our new branch dot size equal to a vector3 dot new. I'm going to say new length for the x, and then new width for the y, and then new width for the z, because we need to decrease it in both widths so it still maintains its square shape. Now, you'd think you'd be done, but if you run it, you get this odd issue. Like, why are there gaps in between the bottom branch and the middle branch? It looks kind of odd, doesn't it? That's because if we were to inspect one of these branches and we go to the pivot, well, it doesn't actually show you the pivot, but the pivot, its position is still -2. So the pivot didn't actually move. So the pivot's floating in space somewhere out here, and it didn't move. So yeah, so look here, you can see where the handles are. This is where the pivot is relative to this block up here. That's not right. We need to edit the pivot offset to match the new width. So what we're going to do is we're going to do new branch dot pivot offset equals CFrame dot new, and then we just have to make this a CFrame because the pivot offset is a CFrame, but really we're just changing the position. There's no rotation. We're going to do a new vector3, and we're going to do new length divided by 2, or you can do times 0.5, doesn't really matter. Because if you notice, let's take this one as an example. This is honestly exactly how I did it, just by trial and error, just by looking at things. So this block is 4 units tall, 4 studs tall. Its pivot offset is -2. So it's -1/2 of 4. So we're going to divide it by 2. We're going to make it negative. Boom. And then we're just going to set the other vectors to 0. You could also accomplish this by using, the other, like vector3.x-axis. Up to you. Doesn't matter. Whatever floats your boat. So this should get us to where we want. Cool. There we go. So now it actually looks, again, more tree-like. And again, the branches, like, so some of them leave a lot to be desired, but I think it looks good enough. It's good enough for me. Like, could be better, could be worse. I don't know. Good enough for me. So we are actually, basically all the way there. We have a tree shape. We have everything that looks good. The only thing we need to do is add leaves. So let's go create our leaf block. I'm going to do a sphere. You can do a cube. I don't care. Up to you. We're going to make this a green color. That looks good. Do some leaf action. I used leafy grass. Do whatever you want. Up to you. Make sure that is anchored. I'm going to name this leaf. I'm going to put this in server storage because this is one of those things where you don't really need to see it. It can just live in server storage. It'll be fine. And then I'm going to reference it up here. So let's go get server storage. So game, get service, server storage. Then our local leaf template equals server storage.leaf. Cool. We got our leaf. And then what we're going to do is we're not going to spawn the leaf with the branch. I mean, you could if you wanted to add some like special leaves, like whatever. I don't really care about that. We're only going to spawn the leaf at the tip of the branch. It's sort of like how a normal tree works. It's more nuanced, but we're approximating a tree. We're in Roblox anyway. So we're going to do it in the base case. So if you remember, the base case is where the like leaf or like where like the tree stops. So it's going to be at the tips up here. And that's exactly what we want. So before this return statement, we need to actually do our leaf creation process. So I'm going to say local leaf equals leaf template clone. And now you're going to notice why we have the pivot and origin here, because the leaf actually needs the pivot and origin to know where it should go. So we're going to do leaf pivot 2, pivot times origin, and then leaf.size, we're going to randomize it. So it's going to be equal to leaf.size times math.max 0.3, and then we're going to do math.random times 1.5. So basically, this is, I don't think there's a good way. I might be mistaken. Math.random might have an override for this. Yeah, it probably, I don't know. In my experience, math.random is good for integers, leaves some to be desired floats. So we're doing our little old like bespoke math.random. So this returns a value between 0 and 1. We scale that to 1.5. So it returns a value between 0 and 1.5 now. And then we take the max of that. So basically, if it's too low, we just clamp it to being 0.3. Works fine. There's better ways to do this. It's another way to do it. Works fine. I don't really care enough. So now we're going to set the leaf.parent equal to the parent branch. You could also set it to the tree. Doesn't matter. Just easier for bookkeeping purposes. And since the pivot is initially at the center of the sphere, this should just pivot it to the tip of the branch. And let's try it out. Wow, look at that. We get a tree. It's kind of an ugly tree. Let's do it again. I want a better roll. Give me a better roll. That's a little better. This is a pretty good tree. So you can see this is not great, but it looks like a tree and it's randomly generated. And if you guys, this is an exercise left up to the reader, if you guys want to, you can expand on this, make sure it's better. So just to recap, the parts that you want to edit are the droop angle calculation and the random branch generation calculation. And if you really want to get into it, you could make, different tracking for the trunk versus branches. You can make branches spin off the trunk and then get to like twigs and have like different levels. And then you can even use like meshes to make seamless like branch transitions as well. There's a lot that you can do with this to make it look a lot better. In addition, you can make the leaves look better. The leaves are like really low effort. I'm not going to lie. And you also note, this is a fun little thing. Since we have this random branch generation here, there might be multiple leaves on the same branch, but you won't be able to see it because they're all on top of each other. So that's also something to note, which is pretty funny, but pretty cool. And yeah, so that is about it for this video. I hope you enjoyed my return to YouTube, at least for one video. And I hope you enjoyed me being on a Mac because I'm finally using my school laptop instead of my computer, because I realized that my laptop for school is actually a lot better than my computer these days. So it works out well. But yeah, I hope you guys enjoy this kind of like interesting tutorial style where it's more iterative. Like you don't get to the end goal; it's kind of teaching you how to get to the end goal. But yeah, let me know what other videos you want to see in the comments. Let me know what algorithms that you use to make this look prettier, because my ugly tree leaves a lot to be desired. But I hope you enjoyed, and that's about it. I'll see you later.